Our today's topic will be statistics, which is the first step in learning the various mathematical procedures required to handle various data, algorithms uh, related to the machine learning, deep learning, data science, etc. All right. So to start with, we'll do a little bit of a programming today. We'll start with the programming aspects, and we'll try to recall many things which we studied, which we already have implemented when we looked at various tools of Python, such as NumPy, Pandas, etc. Okay, we'll have a quick look at some of the basics required so that we can go ahead and learn the statistics. Before starting that, we need to recall something. All right, so let's start the coding. So we'll start with the importing the various tools. All right, so I'm going to import NumPy as NP. Let's import SciPy as SP, and from SciPy I want to import stats. Okay, so the statistical tools, statistical functions are present under the SciPy tool. Okay, and I also want to import the pandas. All right. Okay, so we are running that now. So let's try to have a quick recall of various topics. All right. So this is the first part. Already we know this. If you know, you try to get the answer by yourself, or if you are running a system parallelly and you're trying to code, right? You can try to code this by yourself and you can try to get the answer. All right. You don't have to tell me the answers. Okay. And you try to get the answers by yourself, and you think about this. All right. So it's just an exercise. Those who, right? It's just, we are trying to recall what we already have done. All right. Okay, so that's the, so this is a question. All right, so 5 people play golf, right, at one hole. Their scores are so and so, whatever you see there, they're the scores. So I want you to find out the mean, median, and mode of this, right? So I hope you can recall what we had discussed about what is mean, what is median, what is mode. All right, so this is a fundamental thing required. That's why I'm bringing this. Let me say A is equal to, I'll try to code in my way. This is not the only answer. Okay, you can definitely try to write it in a different way. Yeah, so what happens when you try to bring the stats? Stats is available as a keyword for you. Otherwise, you have to, if you don't import the stats, you have to use it as sp.stats dot something, right? Just to save some time in typing, I'm just bringing the stat value. Okay, you have a facility to load the sub modules present in under a main module. Okay, so that's why we are using it. Okay, so let's write it. So 3, comma 4, comma 4, comma 5, comma 7, right? So that's the data we have. All right, and let me calculate one of them directly. Print. I'll try to display mean equal plus, I'm going to get the answer in a numerical format. I need to convert that numerical format into string because I'm already displaying MEAN, which is the text data. All right, so this is NP dot mean of say A. All right, so let's see what we are going to get. Okay, so the mean value equal to 4.6. Right, I also want to print. Let me go for a median. Median equal to Then I will concatenate this with the casted string format of np dot median. All right, I'm going to call that, sorry, not to a. So median is 4 as per the definition. 4 is repeated twice, so 4 will be considered as median. And then we go for print mode mode equal to plus. Now the mode is not available in the numpy, so I have to use stats dot mode of a. All right, so we are getting the answers right like this. Now I'll go ahead and I'll post another question. Try to find an
Sir, I have
answer.
one small question.
Yes, sure, please.
Sir, actually, I've just joined. So, can you please just give me a small gist of what exactly we are doing, sir?
No, we are trying to recall what has been done already. Okay, this is just a practice session. Okay, so if you are doing the coding, you can do along with us. Otherwise, let's you see and try to recall what we have done. So we have done the mean, median, mode, etc. already, right? So we are trying to recall that. That's all. All right. So this is the next question, right? So there are various crystal lengths possible. Okay, so this is the data set of the crystal lengths, right? And the question is to find the standard deviation. Again, so we know we have studied the equation, we have seen what it is, we have seen examples, etc. This is just a practice for you. All right, so let's try to build the answer, right? By the first, let's try to type. So there is 9, then 2, 5, I guess. Okay, then we have 4. Okay, let me copy it from here itself. Maybe that will save some time. Okay, that's the image. So yeah. Okay, so that's a B. And if you remember, there is a np dot standard deviation as a call. You can call this variable. Okay, so you get the answer. Right. Then, so that's the second thing which you should be able to recall, right? Because we already have come across this. Now, let's go to the next question. All right, so you have a data frame given over here, and the question is to find out the variance, right? So they mentioned that inside the data frame, we have a series called the salaries. All right, so that's the requirement. All right, so let's create the data frame first. All right, so data equal to pd dot p dot data frame. So in order to, okay, there's the format should be followed as per the given this thing. All right, so salaries, after this, let me this and create an array or create a list according to this. So keep entering the values. Okay, I'll just copy and I'll paste from here. Okay, so these are the various values. And so how do you find out the okay, so the question is to find out the variance, but I'll try to make sure that you understand the mean as well. Okay, so I'll do the mean also along with the what has been asked. Okay, so first let's go to the variance because the question is to find out the variance of this. All right, so that should be, we have two techniques. First one I'll show you, data dot. We have, when you press B and press a tab, it should show you. Yeah, so you can check that whether there is a function called variance. Yes, you have a function called variance, and you can do this to get the answer. So this is one answer. Salary, so the variance is this 3.24 E plus 0.8, which is 10 to the power 8. I'll show you the answer in a different way as well. So that is data dot, we can use a dot notation as well, right? So dot salaries dot variance. Okay, yeah, this will also work. So which it's just a different programming way, that's all. So if you are comfortable using the dot notation, go for this. You are not familiar with the dot notation, go to the first technique. All right, so just an option, whichever you want, you can use. So only the question is about the variance, but let's do the mean as well. Okay, so we can do the mean in the same way. Data dot salaries dot mean. So what are the various functions available? You can actually check after you press a dot, you can go for a tab, right? Press the tab button on the keyboard. It will give you a list of all the functions which are available, right? You can use it. So this is the mean we are getting. Again, I'm using the pandas over here. You can also use the numpy. I'll show you the other version. That is np dot mean is the function. You just have to specify what data you want to pass, okay, to this mean function. So what is the data? Data should be coming from this particular data frame, which is data. All right, so data dot in data, I'm looking for a specific column called salaries. Inside that, I am supposed to pass all the values of. So again, it's a requirement of numpy. So you can pass the values. All right, so that's this. So you see, you get the same value, right? So output at the line number 8 and line number 9 are same, indicating that irrespective of which tool you are comfortable with, you can call it and you can. Okay, right. So this is the first part which I want you to remember. Okay, recall the concepts. Yes.
So can you please explain line number 6, in which we have given data dot var, and then we've got salaries and flow 64.
Yeah, sorry. Line number 6.
Data dot.
Line number 6.
Yeah.
Yeah. Okay.
Yeah. Line number 6. Point number 2.
Yeah. Sure. Line number 6. First line, I'm passing the data. Okay, I'm creating the data frame, and I'm calling the function called calculate me the variable, the variance. All right. So data dot var. It actually results in, this is the answer, okay, of the variance. So the same answer is here, but represented in a different format. Even I called in a different way, you are getting the same answer. So salaries is what is the heading or is the name of the series, which has whatever I ask. I ask for a variance, so the answer is this much. That's what it is saying. It is a data type. It's a floating point, 64-bit representation. That is how it is stored inside the computer. It actually gives you that answer as well. Okay. All right. So that's the first part, which is necessary for all of us to recall before we go into the statistics. All right. So,
sir, for NB dot mean line number 9, we can only put data also, right? It will give us the answer.
Yeah, it is expected to give an answer. Okay. Only when you have only one column, we can expect. Yes. Perfect.
All right.
All right. Let's move ahead and. All right. So the next thing which we want to recall, okay, maybe this is new for some of you, but definitely this will be covered again when we move into the probabilities module at a later stage. But we need a part of it to be used, so it's not nothing complicated we are taking from there. Okay, it's the one which we all know, right? Okay, so that is the distributions, probability distributions. So we will quickly try to have a recap of that. Yes, please.
So in line number 3, we have said we called NumPy mean data salary values, and what is that mean? It is no. So in line number 9, right?
Line number 9. Okay.
Yeah. It is basically mean of data salaries and values. So how we have
Go
got
to the
this
pandas. I'm asking the machine. Go to the right data frame by the name data. Data is the name of the data frame. In that, go to the particular column called salaries. Dot. Right. You take all the values from that and get me the mean. That's what is the meaning. Okay. Right.
So what is values, not values, not values?
Every value present in that column. Okay. Every entry. All right. So we move ahead to the probability distributions, right? So we have the fundamental idea that, right, whenever a event is happening, right, events has certain results like tossing a coin, head and tail. There are some probabilities associated with them. So if you try to plot what value, what probability, right, you get a graph, right? So those graphs are considered as the probability distributions, right? So I will plot and show, right? So we have certain objectives, right, behind learning this, right? First thing is that we need to be able to identify what is a continuous distribution and what is a discrete distribution, right? I'm going to come to that, right? So the second objective is that we need to understand, at least we should be able to recall that, okay, there is something called as a binomial distribution, Bernoulli distribution, Poisson's, normal, etc. Many distributions are there, right? Depending upon the result of certain experiment, right, and what values those probabilities can take, right? Already researchers have classified them into several categories. All right, so we should be able to recall, right? Ideally, people should be able to recall the equation, right? For most of us feel it difficult to understand, recall those equations, right? So anyway, we can refer them whenever we want. So what is expected here? You should know that, okay, what is Bernoulli look like, right? What does the normal distribution look like? What is its feature? What are the characteristics? We should be able to recall that. Then, right, our next objective is to create and plot and visualize those distributions, right? Right, again, later on we'll move ahead and we'll apply all of them together into a theorem called as a central limit theorem. So today we are not going to cover the central limit theorem part because that comes under probability, but anyway, so the overall learning objectives are like this. All right. Okay. So with that introduction, we'll move ahead. So before going to the exact concepts of the distribution, we need to remember something. Okay. So we need to recall some of the terms that are very much necessary, right? Before we go into the statistics part as well. So I'm going to give that now. Right. So, right. So we need to remember the various terminologies present, right? In the whenever we try to study the topics, either it is related to the probability or it is also related to statistics. So the first term is like the random variable, right? So a random variable is, as the name suggests, it's a variable. You can assign any value to that, and it is random. There is no restriction and you cannot control what value it is going to take. So it's a numerical variable. For example, let us say I'm tossing the coin 2 times, right? So I can get head head, head tail, tail head, and tail tail. Correct? These are the options. Now, if I try to collect, I'm doing the experiment, I have a result. I'm trying to calculate the number of heads, right? So what are the possibilities, right? Possibilities could be 0 because you may get tail tail in the answer. So you see there is a random variable coming into picture. The result, whatever you have obtained, we are converting the result into a number, right? Again, you have to have a certain rule here. If at all your question was to calculate the number of tails, then your answer is 2. But my question was, I am trying to identify the number of heads we get. right? So one possibility is 0 when you get tail tail. Next one is head tail or tail head, right? What is the answer? It's 1, right? You don't say 1 comma 1, not required. Just say 1 because there is a possibility that, right, I may get head tail or tail head. In both the cases, number of heads equal to 1. Right. Then the other case comes where head might be the answers, where your answer is 2. Right. So you see, you are trying to convert the answer of a random experiment. You are converting that into a number. So whichever variable holds that value, right? The number of heads equal to, you can give it to some value, say x equal to, right? X equal to 2 means you got head. X equal to 0 means you got tail. X equal to 1 means you might have got head tail or tail head. So our intention is not to look at this example now. You should consider there is a variable capital X which holds the number of heads we got in an answer. So that is what is the random variable which you see, right, as a first point. That's the first terminology you should remember. Okay. Now, if this random variable is going to hold only the discrete values, like the example I gave, there is no 1.5, there is no 0.5. In this result, you may get 0, you may get 1, you may get 2. See, discrete numbers are there, no 1.5, no 2.5, etc. So because of that, the second term in the list comes into picture, discrete random variable. So it can hold only the discrete. It means the experiment which you are considering is going to result in the discrete sense. That's all. At the same time, let me give you another example. I'm trying to measure the height of the students in a class. Now you see the answer is not necessarily just a whole number, no, right? I may get, right, maybe measuring in centimeters, I may get 145.3, 149.6, 149.35, like that. You see, any numbers are possible. Each and every number, a real number is possible. It's not necessarily required that you should get the whole numbers always. So now you see the random variable which holds all the possible values over there. It is going to be, right, continuous variable. It can take any value. No restriction saying that, okay, after 2 only 3, after 3 only 4. No restriction. 2 is there, 2.1 is there, 2.15 is there, 2.1555 is also there. See, it can hold each and every value present. That's why we call it as a continuous random variable. Right? So next one is called as a population mean. So population in the sense, let's say I want to do an experiment, right? I'm considering many values, right? Maybe it can be a poll, right? I want to go for a poll, right? So when I go for a poll, I want to give a exit poll result. So I will not ask each and every person, each and every voter over there to say that, okay, what's your vote? Who is going to win? What's your vote? I'm not going to ask everyone. I'll ask randomly 1,000 maybe from a particular constituency, right? And I will be able to give you a guess that, okay, this party might win. Now, out of so many people present in my constituency, I asked only 1,000. You see, right? So what is the average answer you get is the population mean. All right. So you have a group, right? That group you considered for some experiment, right? And you try to calculate the mean of that. That's what is a population mean. Okay. Then we have same thing. Consider a population. The word population is going to come n number of times now. So population does not refer to the actual population, what we think. It's about the count of people, right? It's not just that, it's beyond that. Okay, so population standard deviation is the standard deviation corresponding to a certain, right, a group of objects which I consider, right, to do an experiment. All right. So then that's a population. Then the sample standard deviation. So I consider, right, a small group, and a part of that group I can consider, I will call it as a sample, right? I can try to calculate the standard deviation, mean, etc. of them as well. Okay. So these are the basic terminologies we are going to use several times. Okay, so with that, we'll move to the next topic. All right, so that is, we'll look at the probability, various types of probabilities, various types of random variables coming into picture. All right, so this is the next one. So here we can see a distribution, right? Distribution basically refers to if we are calculating the probability and we are plotting them, right? It's called as a probability distribution. Corresponding to the distribution, as we already have discussed, the variables can be discrete or the continuous. If you have a restriction, right, on what values you can take along x-axis, horizontally I have restriction 2, then 3, then 4 only. No middle real values can be taken. If that is the case, the plot is going to look something like this. All right, so that is a discrete random variables probability distribution. Right, at the same time, right, I have another part where I gave an example like height of something, or I'm trying to measure the length of the phone calls, right, that are being, right, made within a given time, like 6 p.m. to 7 p.m. I want to measure all length of all the telephonic calls, right? You see, it is actually, right, it's not a discrete one, it's a continuous one. It can take any value, right? 3.99 seconds, 3.86 seconds, right? Like that. You can even measure in a different format. But anyway, so you understand that it can be any length, right? So that duration is also going to be a continuous variable. So, right, you can plot it. So,
Sir, can you please increase the font a little?
sorry,
Font
size. Let me check. All right, just a second. Is that fine? Okay. All right.
a little better.
Sure. Okay. So this is the first part. Now let's look at the discrete and the continuous probability functions in detail. So the discrete probability distributions, right, is nothing but it can have a countable number of values, right? So whenever I say I'm measuring something, it should show you a specific number of or a specific value. The value should be countable. So countable number, if you have, it's called as a discrete, right? So that's what is the meaning of the first sentence that you see here, right? Now, how the values are distributed. For 1, you have so many count. For 2, some other count. For 3, some count. So the value, magnitude, whatever you have there, right? So that becomes a random variable because you're doing a random experiment. So for example, if you go to the head tail concept, right? So head might come out of 50 times, head might go for, right, 28 times. Remaining will be the tail. So this number, whatever you plot, is a random thing, correct? So that's why that particular plot is called as a probability mass function, PMF, right? It's a probability distribution of a random variable. How the distribution has been plotted over there, you can actually measure that. All right. So at the same time, when you come to the discrete probability distribution, right? Distribution is a plot like what value, how many times. Okay. So that is actually referred to as a CDF, cumulative, right? You keep adding the previous value. Value equal to 2 is some value. Value equal to 3 is equal to all the values till 2 plus the value of 3. So it's actually cumulative. You accumulate. So that's how we are trying to calculate this particular value. Anyway, so as of now, don't go in depth, right? We'll be going through this in detail when we go to the probability part. All right. So just try to understand. If it is, you think it is too much, no problem. Okay, I'm not going to touch this in the statistic part as of now, but it's a basic. Okay, right. So examples are what are important for, right? So you consider what are the possible values a random variable x can take, right? Whenever a maybe the coin is tossed, right? I have given the same example here. Okay. So whenever a coin is tossed twice, right? You can have the values like 0, 1, or 2, correct? At the same time, you don't have any values like 0.1, 1.6, etc. coming into picture. So because of that, the distribution becomes a discrete thing. Yes, Niranjan? Yes, Niranjan, any question? Okay. So let's move.
Sir,
Yeah, listen.
hello. The way you show the graphs, right? One with a discrete and one with a continuous. So can we differentiate it as a digital and an analog signal? Like the digital goes like this and the analog goes like this.
Yeah, just for understanding purpose, yes, definitely you can. You can. No issues.
Okay. Okay.
All right.
Thank you.
Okay.
Yeah.
Yeah. So fundamentally, that's the difference. But in the explanation part, I have written few more points as well. All right. So just those who are comfortable go through that. Otherwise, just remember these two graphs. Okay, discrete looks like this, continuous looks like this. That's what we want. All right. Okay. So let's move further. I will also show you some points related to the continuous probability distributions. Right. So basically, the continuous distribution can take any possible value. All right, it's going to be continuously plotted for each and every value that is present on its x-axis. All right, so that's this. Right, so it's a plot of the probabilities of the continuous random variable, because of which we are going to call it as a continuous one. Okay, so there is a part which is called, that plot itself will be considered as the PDF, probability density function. What value, how much? What value, how much? That's the density, right? So that's first thing. And another part is there, which is called as the cumulative. I can accumulate, right? All the past values, right? What is the value of the probability which is equal to 1 or less than 1? I can actually accumulate. Right? Again, this part we are going to visit at a later stage. As of now, don't worry. Right? Look at an example. Right? So the example could be here. The example given is the weight of a citizen, right? Of maybe a country, right? So this can take a values, right? Even the decimal point is valid, right? 34.5, 47.7, etc. Right? So we have some of the probabilities which are discrete, you can see above, right? I didn't read it, but hope you have read that. So Bernoulli's, Poisson's, binomial, geometric distributions, etc. fall under the category, right? And that category is the discrete, right? If you plot any of those probability distribution function, right, we will be getting the discrete lines only. At the same time, the continuous probability distribution, right, are of the following names, right? Normal distribution, uniform, chi-square, exponential distribution, etc. There are many distributions, right, which are under the continuous category. Similarly, we have many other probability distributions which fall under the discrete category. All right. Okay. So now I'll move back to the programming part itself. Okay, so I'll slightly reduce the size, maybe otherwise I'll not be able to show you everything. Okay, now let's go to the plotting part. All right, so the plotting part begins with the various types of distribution. So for that, let me I think I have NumPy, SciPy, and pandas are done. Okay, let me bring in some more tools required from the various libraries. Okay, NumPy, I think I have done. Okay, I'll import others. Import the matplotlib dot pyplot as pl. Okay, I'm also going to import say Seaborn I'll bring the CBOM. Okay. All right, and this is done. Okay, let's get the math part. All right. Import math, and yeah, so we already have a SciPy, but from SciPy I have stats already imported. Okay, so since stat is there, all the distributions are there, but what I want is I don't want to name them every time like stats dot something, stats dot. So what I do, I'll do like this. Okay, from SciPy dot stats, right? I'm going to import. This is optional. Okay, so if you can type scipy.stats.norm, scipy.stats.bernoulli, etc. Every time you can type means yes, don't need this, simply import scipy. Okay, so import, this is for binomial distribution. There is another called n by norm. I want Bernoulli's distribution, Poisson distribution, then normal distribution, uniform distribution. Okay, so that's what I want. I think I have almost everything what I need as of now. Let me see. If I need something, I can get it later. So then, yeah, we have a geometric, right? So let's go for that. So that is from numpy dot random. I will import geometric. Okay, then yeah, that's sufficient for me as of now. All right, so let me run this. Okay, so we have this now. Let's directly go for the normal distribution, right? I have a variable x and I'm going to plot the probability f of x, right? So the normal distribution has a specific format. All right, so anyway, the equation is necessary for us. I also, with that, I will say, I'll try to paste a question as well. Okay, let's try to answer the question in terms of as a part of this exercise. Okay, right, so this is a normal distribution. I'll just for your reference, I'll try to increase the size. Okay, so just see this is the question, right? In the sense, I want to plot a normal distribution ultimately, right? I have given some details of that, right? As of now, my fundamental question is, how do I plot, right? This function f of x is equal to 1 by root of 2 pi sigma square e to the power minus of x minus mu divided by 2 sigma square, right? So if you know what is the mean is denoted by mu, and the sigma square, right, is the variance. So sigma becomes the standard deviation. So you see exercise 1, there is a question, plot the normal distribution of size 10,000. There will be 10,000 samples. Okay, what is the mean of that sample? Mean is equal to, mean is given here. You can see that mean is 0, in the sense the mu value what you see here, right, in this equation, that is 0. And standard deviation is given. Standard deviation refers to the sigma square which you have written, the sigma value. So sigma appears twice in this equation. Okay, so we have twice the sigma coming into picture. All right, so we want to code this, right? Saying that we want to plot and visualize this, right, for 1,000, sorry, not 1,000, I think 10,000. Okay, for 10,000 samples, plot the normal distribution. So first, let me do this. Let me create a mean. Mean, it is said that mean is equal to 0. Then they also have mentioned that take the standard deviation as 1. Right? So you remember, mean is the central value. If whatever I get, it should be centered at that mean. And the variation around that should be 1. That's what is the meaning. All right. Okay. Then that's a standard deviation. We created that. All right. So let me create the data. We should create the 1000 samples. Okay. So random samples can be directly created by using this function. Already we have, right, imported the norm. Inside norm, there is a randomly generated, random generation is possible. Okay, so that is by using RVS. There is a function called RVS which generates the required number of data points under the norm category, normal plot. Okay, so I'm directly calling that here. So let's do that. So I'll call it as data normal. That's a variable. All right. So data normal is equal to norm dot rvs. Right. So randomly I'm creating that. Right. So I just have to specify what is the size. So this is the format in which you need to enter. Okay. So how many samples they're asking in the question? They mentioned that create 10,000. All right. Right, then you need to specify a variable called location. That should be the mean value where you want. In the sense, where do you want that curve to be present? It's about the center. So center value means it is mean. Okay, so mean I'll pass, and also you need to pass another variable parameter called scale. So scaling happens by what is called as a standard deviation itself. So I'll just pass that. Okay, so this is the one which creates 10,000 samples of the distribution. Right, then we go to the plotting part. Anyway, I'll directly try to plot it. SNS dot, I think I can call it dist plot. Right, yeah, dist plot is there. Plot this for the data normal. Let's see whether we get, yeah.
So this norm.rvs stands for?
Yeah, it's a function, inbuilt function to create the random variable. Okay, random values, not variables, my mistake, random values. So of size, whatever size you specify. All right. Location stands for where is the center. So central value is around mean, that is 0. And the spread is controlled by the STD value, standard deviation. Okay, so this is the first part. Now I would like to extend further. I want to show you that, see, I have never used the equation, right? So this equation, what is there, I have never used. In this case, it is a built-in part, but I don't want to stop here. I want to go ahead. I want to do something more. Okay, so I will add something to this. So what I do, I'll try to create, I have an X value, I have some range over there, right? For that, I'll try to create these values, right? By using the function, right? That is given here. You can see f of x equal to something given, right? So I will use that to create this plot. X value, if I use this equation, I should be able to show you that even if I use my own method, I still get the same because this is built in, right? So people may say that there is a built-in function, it will generate directly. How do I justify that? Even I can do that, right? By using this given function, right? I should be able to do that. All right, so let me do that. Okay, so first I'll create a data frame. Maybe it's again, multiple options do exist. People can code it in their own way, right? This is just my way. All right, so I create data frame. Maybe I'll call it as a normal n is equal to td dot data frame, and I need say a name to this. I'll call that as a x. All right, and x will hold all the values of this data normal. All right, so that's the first part I need, and then I create for each of these x value, I'll create a probability associated with that. All right, so that is you see we are using the various aspects we studied in the panda. I'm going to add a column now. All right, so df underscore n of, I'm going to call it by a name p, for a probability. Okay, so I have a data frame, x is already there, add a column to that. All right. So this is equal to, so df underscore n, that's the name, right? For all the value present in X, I want to do something. So I'm adding a column based on the values I have along X. For every X value, I have to do something. So use the X and do something. So how do you do that? You can write a lambda function if you remember. All right. So that is X dot apply something. So there is a method apply, and apply can be applied in a general way, right? How the general way, it's called, you can call it as a lambda. Okay, lambda of any variable you can take, because this variable has nothing to do. Anything you pass, it will work on that. All right. So now I should be carefully, I should write that equation, right? The f of x equal to 1 by root of 2 pi sigma square. Whatever you see here, I should write that here. Okay. So let me try to write that. Correct me if there will be, if any mistake comes, you observe. So first I'll start with, it's a e to the power. First I'll write the e to the power part, which I find it very difficult. So e to the power, it should be np numpy dot exp, correct? E to the power. There is a negative sign, e to the power minus of x minus mu, right? So what I am supposed to do, minus of, I have a x there, I have subtraction, then the mean. So okay, I need these many brackets. So v minus the, right? Anyway, I know that mean is 0. I can neglect that, but still I'll write it. Okay. So v minus mean x minus mu divided by, right, the 2 sigmas whole square I'm supposed to write. Okay. So x minus mean, first I divide by sigma so that I can square it. Then I'll divide that by 2. Okay. All right. X minus mean divided by the STD. Okay, so then this needs to be raised to the power 2 x minus mu by sigma the whole square. That is done. After this, I should divide it by 2. Okay, so divide by 2. All right, then it is closed. So that whole exponential term, e to the power something we had, right? That is there in this particular part, np.exp, everything, we closed it, right? After that, you see there is a division, root of 2 pi sigma square, right? That's what I'm supposed to further calculate. So what I do, I'll divide by, okay, so divide by 2. Okay, so brackets will see. So this bracket is closed. Let me check. Yeah, that bracket is closed. So I can simply divide this by, right? I'll use another bracket. So this is the STD. That is a sigma. It's a square, right? So square root of what I'm supposed to use? 2 pi, right? Okay. So first I use the sigma square under root. Under root, the sigma square becomes simply sigma. Okay. So first I use STD. Right. To that you multiply with square root is under numpy np dot sqrt. Okay, so square root of for this, and we'll be writing the 2 pi. All right, so 2 into np dot pi. All right, so that's done. I just have to close, I think, one more bracket. Let's see. Right. Okay, let's see. So that's the whole equation corresponding to f of x, right? Right. So that is done. Right. Okay, let's proceed further. So in the next step, what I want to do, I want to sort them, right? That's an optional case. So df underscore n should be equal to the df underscore n dot. So there is a function called sort. You can simply type this and check so. Press a tab. If it is there, it will show you. I'm expecting a function. Let me check. Okay, yeah. There has to be a function. Yeah, sort let me write. Okay, so sort underscore, I think sort values will come, right? Sort, yeah, sort values you can see here. So the values can be sorted. You can actually specify by which variable. According to X, I want to sort, because X is increasing, right? Along the horizontal axis, X is minimum, X increases and X goes to the bigger value. So by, right, I will have to specify by which one. So by X, right? This will do that. Now I'll plot something on this graph, right? Which is the graph that I am going to obtain, right? Not the built-in. All right, so let's do that. So that will be done by using, now I'm not using the C-ball, I'm going to use the matplotlib itself. All right, it's a simple plot, right? You try to plot the df, and in that first you plot the x. Okay, that's along one value, and the df underscore, and say I want to plot the p values. Okay, so the p, I'll say that give me a plot of maybe I'll try to say a dash. This should work, right? Then right, plt dot show. Right. Let's see what we are going to get. Yeah, so you see there are actually two plots. The previous plot was properly the blue colored one, right? So the blue colored graph is actually visible over here. In this portion, you can see a blue color, right? That is slightly different than what we are getting. What we are getting is this outer graph. So the values which we obtained, the 10,000 values we obtained from the built-in function, right? Those are actually plotted, right? That have been covered with the graphs which we have created. That is actually matching. So saying that the ultimate point is this. So if you use this equation, right? So whatever equation that you see here, right? That actually is a distribution function called a normal distribution function, and whatever is the range that you give, provided you know what is the central value being and the standard deviation or variance, if you know that, right, you can use it, right, to create this. So the point to remember, I prefer people to remember this equation when I say normal distribution. Yes, not possible for everyone because we have many things coming up. At least I want you to remember this graph, saying that, okay, what is the normal distribution looks like, right? If at all something comes, yes, this is what is the expected answer. You should be able to think that, okay, this is how it's going to look like. Possible? I hope that should be possible. At least to think of, right, what is the curve looks like, right? We have many graphs coming up, irrespective of what type of graph we are looking at, right? So graph will be different so that you will be able to recall. Yes. Please go ahead.
So, sir,
Yeah, Gaurav.
How we
so the both functions gonna do the same work, right? But the second one is what we say, emphasized on the function, the equation part, right?
Yes.
Okay.
Second one is
So,
equation.
sir, okay. So, sir, normally, what what function do we should use? Like the first one or the second one?
No, it's
Because
left to you. There is no rule saying that this is the one which you should use. No rules like that. You
okay.
choose. My intention here is that you use the built-in one or you generate yourself. Both are same. That's what is my idea here. Okay, I just want to say that, okay, I gave an equation. I have to justify that yes, this equation can do the job what we are intended to do. That's all. Okay. Yes. Next question, please.
Sir, which are the two functions? Sir, basically we have just talked about. I guess the one function is the normal distribution.
Yes. Only the normal one we have used. Okay.
So which one was the other one which Gaurav was mentioning?
No. Other one in the sense we see here we have implemented the equation itself, right? We wrote it's a manual calculation. So the automatic calculation happened here, right? it gave all the values. Now we ourselves calculated the value. Both are matching. So whatever is built in and whatever we implemented, both match. That's all.
Sure. 7 line df underscore n function I am not understand.
That's a name given. Just to identify that, it's a data frame of normal distribution. My name, I have given. You can even give any name. Your name, my name,
Okay.
anything will work.
Okay.
Okay? Yes.
Okay.
Yes.
So just one point. So in case of normal distribution, we can say that from mean, the left side and the right side of the part is equally divided, right?
Yes, yes, yes.
So that would be an observation that we need to take care further,
Correct.
right?
Correct. Yes. So,
So,
if you read the sentences I have written just before that, whatever, when you get the material, you read there, it actually, whatever you mentioned is this. Perfect.
Yeah. Oh.
Yes. Yeah. Any other question? Okay. So let's proceed further in that case. All right. So the next distribution I want you to concentrate is the binomial distribution, right? So far, right, we discussed only one. So we'll move on to the next one. Okay, so all right. So this is the details of the binomial distribution, right? So the binomial basically stands for, as the name suggests, bi means only two. It's actually the binary, whenever the experiment results in a binary type of answer, like yes or no type, right? So that kind of like tossing a coin, head or tail. Head can be assigned to 1, tail can be assigned to 0, and you are going to do the experiment on the same result. You repeat it 10 times, 100 times, 1000 times, 10,000 times, and so on. All right. So that particular kind of experiments result belonging to the binary category, right? The distribution will follow a specific by the name. It's called as a binomial distribution, right? So you have only two possibilities, like I increase or decrease, yes or no type, right? So you gain, you lose, something like that. Whenever our intention is to model such experiments, right? The preferred one is binomial. There are other versions of binomial as well, which we are going to see later. But right, so this is the equation. You see, right? The n factorial, right? So let's try to first understand the various parameters of this. I'll increase the size further so that you can see this. Okay, so you see here, what are the various parameters, right? N and P stand for, I'm repeating the experiment n times, right? P is the probability of, say, success. In the sense, if the result is 1 and 0, we can say that 1 is assigned to a success, 0 is assigned to a failure, right? Or you can reverse as well, doesn't matter, right? So just remember what you are concentrating, and you try to stick to the same throughout. All right. So 1 is a success, 0 is failure. 1 is gain, 0 is not gain, right? Not gaining something or losing something, etc. Right? Like that. So if that is our convention, so the P stands for the probability of the success, probability of 1. So that's what is a P here. Out of n different trials, right? So P is the probability of the success of each trial. I toss the coin once. What is the probability of head? You will say that 50%, 0.5. Correct? So that's what is the P. Right. That's the first thing. Right? K is out of 50 times. Let's say n is 50. I'm going to toss the coin 50 times. Out of 50 times, right? Out of tossing the coin 50 times, I'm expecting, what is the probability that I get heads k times? K is the number of heads I'm expecting. In the sense, see, this is the question. What is the probability that tossing the coin 50 times results in 10 heads? See, 10 equal to the k. So n equal to 50. Probability P is equal to 0.5. Probability of head I'm talking about, right? And also K equal to the value I'm expecting. What is the chance that I will get 10 heads when I toss the coin 50 times? So those are the values. F of, so that has been denoted over here. Okay, so that's the equation that you can see here, right? F of n comma k comma p, right, is equal to, this is a notation, don't worry, p of x equal to k, right? Equation what we are concentrating is the on the rightmost part, n factorial by k factorial into n minus k factorial, right, into p to the power k into 1 minus p to the power n minus k. So this is the main equation, and I expect people to remember, whoever can remember, right? It's very good if you are able to recall. Okay, right. Now, let's try to code this. Let's try to visualize how it's going to look like. All right. So let me define the p value. P is equal to how much? It is 1 by 2. Let's say 50%. Okay. So there's a question at the last. You see, consider an event where a fair coin is tossed 10 times. 10 is n value. Okay. And the number of times you get the head is recorded, right? So how many, what is the chance that out of 10 times, whenever I toss the coin, I may get is no head. So k becomes equal to 0. Then k becomes equal to 1 head. What is the chance that you get 1 head? What is the chance that you get 2 heads out of 10, 3, etc. Now we are plotting that values here. So 0, 1, 2, 3, 4, up to 10. 10th value is also there. Out of 10 tosses of coin, all the 10 might be head, but definitely you know that what is the chance? Chance is very less, correct? So anyway, we understand what I'm expecting, what we are expecting as a graph. Let's see whether we are going to get the same thing in the form of a graph when we plot. Okay, right. So let's try to do that. Sorry, I pressed the semicolon because I do the programming in MATLAB as well. So there is a habit of, we need to put a semicolon if you want to suppress something. Sorry for that. Okay, so there is a q value. Q is equal to, this is 1 minus p, right? Then the number of times you want to toss the coin, let me call it as 10. Okay, then so again I'll use the same two approaches we did for the previous case, but I will not stop in the middle. I'll do it completely, then I run it. Okay, so first approach, create a built-in, use a built-in function, create the data. That is one plot. Then we will plot using the second method where we try to create the same thing using the function given, right? Using the equation given. Both will be done here. All right. So the first one, I'll call it as a data of, I'll call it as maybe the binomial. So data binomial is equal to, so we already have imported what is called as a binomial, right? I'm going to use that, and I'll use the same function RVS to create the data set. All right. So this is binom. In the binom, I can call RVS, right? So you just have to specify what's the, how many samples you want. In this case, just 10. Previously 10,000, now just 10. Okay, so that's N P. Okay, so N is the number of things. Again, this experiment can be repeated any number of times. Okay, so N comma P is what I want to say. Then let's try to visualize the data directly by calling SNS dot. I'll try to go with the dist plot. Okay, so in the dist plot, plot only the data which we have created. Okay, so data binomial. All right, so that's the first plot. First part, I'm supposed to expect a graph. All right, I'll not stop here. I'll do the other part, and let's go ahead. Right, so the data frame I'll create, say maybe I'll call it as a B because I'm looking for the binomial, right? So the PD dot data frame, right? It's this will be pretty much similar. All right, so I'll just say that go for create a column X, and under this X I want the data binomial, right? So that will be X is created, the name of the series. Below that we will create the, we'll put all the values. That's all. Okay, so that's what is happening here. Should be pretty straightforward. Then I will create another column depending upon the values present in this. All right, so that is the df underscore b. Let me create a column. A new series is being added. The name of that will be p, indicating that it is a probability. Okay, so only p is given just to identify. We can give any name, doesn't matter. All right, so this is the df underscore p. All right, go to the x, right, and for every value in the x, each and every value in the x, right, I am supposed to apply something, the same logic we have applied earlier. Okay, apply. So function is not defined earlier. If you have a defined function, you can call the function here. I'm not doing that. I'm going to define a function using the lambda technique. Okay, so this is lambda. You pass a variable v to that, and as and when I pass this v to this, right, what should happen? I should write after writing a semicolon. All right, so just look at this. So it should be, right, look at the equation. There is a factorial coming into picture, right? So let me, it's present, factorial is present under the math. Okay, so this is math dot factorial. Yeah, factorial is there. All right, of n, right? Factorial of n comes in the numerator. All right, so after that I need to divide this by something. So divide by, right, I have a denominator. You see, it is k factorial into n minus k factorial. All right, so first k, I think instead of k I have passed the v here. The v represents the k in the equation. Okay, so let's do that thing. I'll bring a k here. So when I pass a k, right, this is what is happening, so that it becomes easy for us to track. Okay, so this is math, the factorial, math dot factorial of the k value, okay, to this, right, I need to multiply, right, the math dot factorial of, so it is n minus k. So I know the n already is there, n minus this value k. Okay, so how many brackets are open? One. Oh, this whole thing. So I need to close this. All right, so yeah, it's already closed. So that's done. So after this, so I have closed 1, 2, 3, right? After that, now you see in the, look at the numerator part. Numerator has p to the power k and q to the power n minus k, right? So p to the power k, that's what I'm going to multiply now. So simply multiply. So this is into, now this comes to the numerator part. So in the numerator, I'll take a bracket. So this is p raised to the power, so star star, p to the power k. Okay, that's the first thing. To this, you also multiply another term, that is q raised to the power n minus k. So write a q there. Q is already defined. Raised to the power, I'll take another bracket. Okay, so that should be n minus k. So let's see how many brackets we have closed. I think all are closed. Let's see. If there is any error, we'll come back. Okay, so that's a function. For each and every element present in the x, right, column, calculate a p corresponding to that. So p will be created according to this. All right, after that, let's proceed further. Now I'll simply try to plot. So plt dot plot, say the data frame itself. So df underscore b is the name, I guess. Okay, in that plot me the x. That's the first. That's one of the axis, and I also want to plot same df underscore b. In that plot me the p. Okay, and let me say I want to plot. Let's see whether this works. If it does not work, I'll change this later. All right, so plt dot show. Okay, I hope you are getting adjusted to the way how we plot things, right? So maybe it may require some time to get adjusted. If you have not started working on the plottings, pandas, numpy, okay, at least start now, so that you won't feel you are lagging when we go to the advanced topics, actual topics, all right, where we are going to use this n number of times without doing any revision. There I may not have any time to say that, okay, this is what is happening. We'll directly keep writing the function. We assume that you have worked already, you know something. Okay, so that's the case, right? So please work hard on this part. Okay, let's see. Oh, there is an error. Fine, let me check that. So in which line? Line number 4. PD dot data frame by. Let me check. Let's see. Data by non. Did I close the brackets? Yes. Data df underscore b equal to pd dot data frame open bracket this data by norm. No problem with the data by norm, right? Okay, there should not be a problem because that worked here as well. 1, 2, data normal. Okay, I understand. I have not given a size. So let's create a size. Let's say that this is repeated, say 10,000 times, right? Because experiment needs to be repeated sometimes so that you can get the so many samples over space, given space. Okay, let's see. I think that's the issue. Yeah. All right. So, okay, it's not matching because of one reason. I said that I want a size of 10,000, but I never said that. Okay, this needs to be raised by so much now. So let me try to 10,000 into. Will it work? Yeah, the samples are coming. Let me check. What's the mistake? 1 by 2, 1 minus p, 10, n comma p comma size. Now that problem is solved, but something else. Let's see. Do you have a warning? Yeah. Plot plt dot plot x. Okay, list plot by. Let me go for, I don't want a KDE. Okay, there is a kernel density, right? So that I can actually. Okay, let's check. Yeah, all right. So we got it. Right. So you can see that even after programming semis many times, right, we also get, right, don't get the things done in a straightforward way. In a single step, no, I'm, though I have experience of more than say 14, 15 years of working on this, right? You see, this is what happens when you do practically, right? You don't get everything in a single step, right? Don't expect that to happen whenever you practice, right? We will make mistake, we all make mistakes, right? But we should have an idea that, okay, maybe this is the problem. That will happen only when you code. Okay, do a lot of coding, you will get an idea that, okay, maybe this is the case. Okay, so coming back to the answer, right? Don't worry about the coding part as of now. That's fine, right? Learn from basics, everything will come in handy at a later stage. So the blue colored lines, what you see, they are the created values, automatically created by the machine using the built-in function, right? So those values are there. Now you see, what is the when you toss the coin 10 times, right? What is the chance that you get 0 heads? Is there a probability? Definitely, you say at least 1 head might come. So you see that is actually close to 0 here, right? So same thing happens with the other side as well. You see, what is the chance that you get 10 out of 10 heads? A random experiment, right? So it's very less. So you see that that's also less. But as you increase, right? So slowly increase. 1, there is a chance of getting 1 head, 2 heads, 3 heads, 4 heads. It says that there is a 50%, it's like at the center, right? So at the center, this is what is the case, right? That will be normally maximum. Again, this looks like, right? It's not a normal distribution, but it may tend to be normal when you increase the number of samples. Okay. So this kind of plot, my intention behind showing this is, right, to show you what do you mean by a discrete sample, discrete distribution which is discrete. Yes, it can take 0, then 1, then 2, then 3, etc. That's the first point. Okay. And the second point is specific to this distribution, how the graph is going to look. Two things you need to understand. Again, in addition to that, we have another requirement. If possible, remember this equation. Okay. If it is not possible to remember this equation, at least try to remember this graph. It is a discrete. Binomial means it is discrete. Start from a lower value, slightly increases and comes down. All right. So that's what is expected when you say that, right? It's this particular distribution. All right. Then let's go for another distribution, right? That is also a very famous distribution that we might be using several times. So that is called as a Poisson's distribution, right? It also has an equation, right? We just have to use that equation to plot.
So, sir, basic difference between normal and binomial is that normal is mainly continuous variable, whereas binomial is in discrete fashion. Both are normal, both have equal number of left and right hand side. It's just that one is discrete and other is continuous.
Yes. In addition to that, I will add a point. What you told is right. In addition to that, normal has this mean. Normal's mean is always 0. Okay.
Right.
Always 0. Right. Here you can have a different mean. Okay. Okay. Other than that, fine.
Yeah. Thank you.
All right. Sure. So the next one is a Poisson's distribution, right? Probability. You can. I'll slightly increase the size. All right. So try to see what is here written here. Probability of k events, right? Probability that k events will occur in a given amount of time. So that's what we want to find. Whenever, right? Whenever we have the Poisson's distribution coming into picture, we need two variables. One is called as a lambda, which is the mean of, right? Whatever you consider as mean, we'll consider that. Okay. And the second parameter is k, right? Like out of, maybe the Poisson distribution can also be can be applied to, for example, I'll give an example. I know that the people make calls between 6 to 7 p.m., right? Out of 10,000 calls, how many calls will last more than 3 minutes? That's what I want to find out. Such things, right? Whenever you have such things in mind, normally we go for Poisson's. Okay, so that's again an application part, right? Right now, don't worry about application. I just gave an example. That's all. Okay. Fine. So now we'll directly try to answer a question here. Okay, so that you can see the question, right? Plot the Poisson distribution having a size of 10,000, given that the rate parameter is 4. That's actually the lambda value which is given. Okay. All right. So now let's quickly write a code for that. Okay. All right. So let me start with the parameter given. Rate equals to 4. All right. That's what is given.
So
Yeah.
10,000 is like number of trials, and what is 4 here?
4 is the mean value of that. Okay. Whatever results you get, result may vary from any number to any number. So, but they have given the value of that parameter lambda. That is 4, right? Now you are trying out of 10,000, right? How many values are, right? Starting from 0, how many can be 0, how many can be 1, how many can be 2, like that we are plotting. Okay, that is the plot which we are going to get. Something very similar to this. You see, previous case we are trying to calculate the number of heads, right? How many heads might come? 1 head, what is the chance? 2 head, what is the chance? 3 head, what is the chance? Like that. That's what we are doing.
So, sir, what is lambda exactly? I don't understand the lambda.
Mean value. Do you understand the mean value of your answers? I have answers like
Yes.
1, 2, 3, 4. That's why I did the mean first. It's a mean value.
Okay.
All right.
Just another terminology for
Yes. Yeah. So once we deal with the practical data, I will tell you how to deal with the lambda. As of now, it's fine. Simply take that. It's a mean value. Okay.
Okay.
Fine.
Okay.
Sure. So I'll create it. The code will be pretty much similar. So data underscore, I'm dealing with the poison. Okay. So data is equal to, so I already have imported the required functions, required modules. So I can, yes, right. So go for rate and the size. 10,000. Yes. Yes. Okay. Then directly call the plot, first plot is equal to dist plot. Right. So I want to pass data, say, poison. That's the first thing. Then you need to, in this case, I will define the number of bins also. Okay. Otherwise, by default, if I get more number of bins, it may look a little bit messy. So just to avoid that, I will go for bins. All right. So bins equal to the number of vertical things that you want to visualize. All right. Let me say that I want, say, just maybe 30 or something. Okay. And I'll do the, I just learned this from my previous graph. I should say that I don't want a KD. Okay. So this is false. Otherwise, I will get the same error. I will not visualize both graphs simultaneously. All right. So the df underscore p, right, standing for the poison, is nothing but the pd dot, it's a data frame. Same thing, right? What I will do here is, okay, go for x, and in the x you put data. Yes. Okay. Then create another new column to this. That's df underscore p should be equal to, yeah, sorry, I have to add a column, right? So I need the variable name of that series which I'm adding, the new column name, right? So this should be equal to df p of, take the values from x, and what you should do, you should apply something. Okay, so apply lambda. Okay, so this is lambda. I will call maybe some parameter, you can say v, fine. Now look at the equation, right? I'm trying to write the equation as it is. So I'll start with the e to the power minus lambda, lambda to the power 4. So the lambda is called as a rate in this question. So we'll start from there. Okay, so the rate needs to be raised to the power k. Okay, so k is the v here. Okay, I think I called it as v. I'll call it as k because it's easy for us to understand. All right, so that is rate, that is lambda to the power k. I just implemented the second half in the numerator first. That's easy for me. Okay, then to this I need to multiply. What you need to multiply? It is e to the powers. E to the power is np dot e exponential. E will also work. I'll show you that. Okay, e to the power. You see the equation? It is minus lambda, so it should be minus rate. Okay, so I think this will close the NP part. Okay, so to this you need to divide by something. So divide by, so what you should divide? It should be a factorial, k factorial. So factorial is present under math. Okay, so math dot factorial. Okay, math dot factorial of k factorial. All right, so I think we have closed this. that closes the lambda apply function. All right, so that is done. So once that is done, what we can do is we can directly go for the plot. plt.plot. So first I want to plot the df underscore p. In that, get me the x along one axis. Okay, and plot p. What do you want to plot? The p itself, right? So p. Okay, again we have a problem. 10,000 is there, so I need to multiply 10,000 into this, and you say that plot these values as. All right. Hope this works. Yeah. So you can see that it's a slightly different. You see, it's right. It's not equally. There is no equal span present, right? So something is shifted more, right? Maybe you have more values on the left, more values on the right, etc. So this particular, what you call, the distribution has a characteristic, right? Like this. So whatever machine generated and whatever we tested with by using the equation given, right, they match. Okay, so the same technique can be applied to, right, many other distributions as well. But right, whatever we need, whatever I wanted to teach you mainly is the fundamental difference between the continuous variable and discrete variable. Okay, so when you get a material that will contain more plots. Okay, so as of now, just understand that, okay, there is an equation and we are trying to implement that. Okay, so in class I will not solve others also. It will simply take time in typing and running that. So as of now, the fundamental idea, differentiation between the continuous and discrete, first thing, and equation corresponding to each of the possible distribution, and a graph associated with that. You just have to remember, is it discrete, is it continuous, what is the shape, what is the equation. All right, so this is what is required, right, to begin with. All right, we will be going in detail in this when we go to the probability and related stuff at a later stage. But as of now, just to enter the concepts of statistics, I must need this. That's why, right, I took the first half of this session just to concentrate on this part. So we'll be going for a break now, and when we come back, we'll start
Sir,
the
please
actual
show.
statistics.
Sir, please show again code.
Yeah.
Thank you, sir.
Okay. So
Okay.
it's a yeah.
One request, please sir, जहाँ पे हम लोग न्यूमेरिकल स्टैटिक्स को अप्लाई कर रहे हैं, कोड इज सो काफी लंबा है तो पूरा आ नहीं रहा है. So can you copy this line and show the text in Excel या notebook?
Yeah. You will get the complete. You will get the actual code only. Okay. I will be sharing you the IPYNB file. All right. So that everything is available to you to directly run. You don't have to type.
Yes.
Okay.
Yes.
I'll be sharing you this. So just remember this name. You will be getting a file by this name, in class coding on this date. Okay, 16/7/2022. We are writing this code in class. So you will get this file as it is. Okay. Simply run that. You will be able to get that. Okay. All right. Any other doubt?
Hello, sir.
Yes, please.
Hello, sir. Particular in this this 17.
Okay.
Particularly in the line 5 code,
okay.
right, sir?
Okay.
So the first part is when we apply the lambda k. So this is the basically in the formula k is basically like in divided form.
Okay.
Right. So first we have I think second part I could understand.
Okay.
Like np dot this is first part. I couldn't understand, sir. We have to put divide by k, no, sir.
This part you're asking about this part?
Yeah, this part, yeah.
Rate power k. You see the equation. So there is a lambda power k, right? Here.
Yeah.
Lambda is a rate. According to this problem, lambda they have given as a rate. So rate to the power k. I should do that, right? So you see here, this is rate raised to the power k. So 2 stars. If you write, it is raised to the power in Python. Okay.
Okay.
So that's what this is, lambda to the power k. I'm calculating this. So to that I'm multiplying with the second part, right? So that is the second part, e to the power minus lambda. So you see, e to the power minus rate. Then I divide by the denominator, k factorial. You see the k factorial here, math dot factorial of k. That's all.
Okay. This factorial means, sir, k factorial means
K into k minus 1 into k minus 2 into k minus 3 dot 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 up to 1. If I say 10 factorial, it is 10 into 9 into 8 into 7 into 6 dot 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 up to 1. Okay, that's a factorial. All right.
no. Okay, sir. No.
Okay.
Good.
Okay. Yeah. Any other doubt?
No, just to conclude this as a summary, so this would be again discrete one, and here the distribution would not be uniform. It would be either on the right hand side or on the left hand side. The weightage would be more. Right?
Yes. Perfect.
Yeah.
All right. So you will be able to find a lot of distributions, right, available. But I try to cover few major ones only because anyway I'm going to send the codes of other distributions also along with this. But I'm not discussing that in this session. That's all. All right. And we'll start with the statistics part. So far, whatever we were discussing, they were the prerequisites. I wanted everyone to be able to recall the major parts of whatever we had discussed. All right. So the objectives of the first part of the discussion is to learn about the following concepts. The first one is called as a sampling. And then we'll move on to the confidence levels. Then we have a third topic coming up, which will be called as the hypothesis testing. And then we'll see the statistical experiments, right? So in each of the topics, we have the subtopics that are mentioned here. So under the sampling part, so we are going to look at the topics called as, right, how do you design the sampling? What exactly is meant by sampling? That's going to come first. Then we'll be looking at what are the various strategies that we are going to apply to do the sampling, and can you estimate something out of it, right? So those are the topics. Like that, we have subtopics under the confidence intervals. We have the significance testing coming up over here. So these are the topics. So first, let's start with the concept called as a sampling. Right. So basically, normally whenever we try to do an experiment, right, so you may have to collect, right, certain data, right? Though the actual data set is huge, right, we may not be able to do that experiment with each and every data point, right? So that's what you can see here. So we call the huge, right, set of data samples, we call it as a population, right? From that, I pick up only certain, right, data points by a process called as a sampling. I take something randomly, like just consider the example I mentioned earlier. In a voting system, I want to predict who is going to win, right? I may not be able to ask each and every person, right? So that's a huge population of a constituency, right? What you do, right? Again, varieties of sampling techniques are there. We'll come to that later, right? Take any one method and you ask, right? Maybe mostly randomly, right? You choose a person and you ask, right? Whom did you vote? And right, if they say yes, this is the person, you hold that data. So that's the sample, right? So sampling is that's one very important right aspect when it comes to the concept of the statistics, right? So it starts with the sampling procedure itself. So the topics to be covered will be, right, as you can see over here. So design the strategy. What are the properties you have with respect to your population, right? The distribution of the sampling, right? Estimator, how do you relate it to a random variable, right? And there are some examples. Okay, all right. So to start with, let's see the designing process of a sample. Now, we have a goal in front of us, and the goal is, right, to perform a survey for opinion poll, right? So obviously, the question is that I want my prediction to be close, or it should be as close as possible to the actual result. Let's assume that that's the only idea behind doing the opinion poll, right? You're doing a survey of that. Now, the first question is that it's related to the sample size, right? If I have, say, uh, a lakh people, right? Let's assume that a lakh voters in the region where I want to do this particular survey. Out of that 1 lakh people, what should be your sample size? How many people you should select, right, for sampling, right? So because depending on whatever samples you get, right, whatever answers you get from the questions you ask to them, right, you should be able to model the whole constituency, 1 lakh people, right? You are trying to model them by using, say, maybe 50, 100 people, right? Looks pretty hard, right? So what is the chance that whatever survey I made, right, is going to match to the actual result, right? So that's actually a tough job, right? So basically this is what we are doing. So first question, right? How do I go ahead with the sampling, right? So from there it begins. So how many people I should? So we'll try to answer maybe at a later stage, but let's try to have an overall idea that what we are trying to do. Then, right, the quality of the samples also matters, in the sense who all should be included, right? It depends, right? So all these kind of sampling, right, depends upon, in the sense, the sample size and the sample quality, right? They are the major aspects when you don't have a huge data data set available for you. Sample size is small. I'll give an example. For example, you consider the medical research, right? So medical research has to be performed on the patients only, right? Most of the cases, right? Again, uh, number of patients you assume pretty less. Out of the patients, only a lesser percentage, okay? Very less people agree to be a part of your research, okay? There is a risk, right? So you see, under such case, right, under the whenever your sample size, you don't have any option to sample. Whoever comes, you should do the research work. So in such cases, right, there is no question of population and sampling. Whoever you have, it's in very less count. So right, a particular disease, you want to find out you want to do a research on that particular disease, and the number of patients that come to a particular research institute as a patient is very less. So in such case, right, you see, you have to perform, right, with the very less number of, so the sample size is less, very small. You should, right, uh, do your research. That's the first thing. So second one example is a customer survey, right? So right, because people purchase a particular product, right? Similar product may be available with several brands, okay? So the number of customers purchasing a particular brand product may be less, right? So doing a research on them, how many of them will purchase if the price is 500? How many of people, how many will purchase if the price is kept more than 600? Like that, you can do a research on it. It will give you an idea about it. So that's why the sampling part is very important, right? So the whole idea is that I have a target, right, to do a survey on the opinion poll, right? And I have to guess that what should be the number of people I should talk to, so that my guess will be closest to the actual result. And that's the first thing, right? To do that, how many people and what's the quality of the sample? Whom should I ask? That's also another question, right? Unanswered. As of now, I don't have an answer. Okay, let's see. Now, so fundamentally, the sampling has several strategies available, right? You can perform this, the samples using many methods. So first technique is called as a random sampling, right? You don't have anything in your mind. So as you know, I'm doing the survey. I'm asking people whom did you vote, etc. Depending on, right, the results I obtain, I may make a guess that this, okay, this party might win. All right, now you see this simple random samples will be something like randomly whoever you meet, you simple ask, did you vote? Whom did you vote? Okay, just like that. I ask question at random. I may skip someone, right? I don't know how I'm going to decide. So I'm seeing someone, okay, let I say that no, I don't want to. Next, randomly I think that okay, I want to ask this person. So I'll ask. So selecting the n number of samples, right, out of your population. Right, I have to decide what is this n as per my previous question, how many samples, right? So selecting n number of samples, right, and we assume that all these n number of samples you are equiprobable, right? Equally, there is an equal chance, right? So like if I do an experiment head tail, I assume that head, how many times head comes, same times tail will also come. This is what I guess. Similarly, when my intention is to do a poll, right, and the opinion poll, I will be doing the same thing. I'll assume that so equally there is a equal probability between people, those who say yes and those who say no. Okay, people those who say that yes, I voted for this party and I voted for the other party. That's what we are assuming, equiprobable, equally probable. Right? Again, right, when I choose someone for as a sample, it should be independent. It has nothing to do with whom I chose earlier, right? I chose him earlier, so I'm choosing him now. No, that should not be the case. It is unbiased, independent. There should not be any bias in the people I choose. All right. So this is what these are the fundamental characteristics of a random sampling. So when I say random sampling, people think that yes, it is the easiest one, but this is not the easiest one. You see, it is ideal, but not practical. So maintaining all these conditions are not possible. I may say that yes, I will be independent, I will be unbiased, right? I'll say that I will see to that equal probability I will maintain. I may say, but it's too difficult to do this, right, practically. So the number one is a simple random sampling, right? So the second technique is called as a stratified sampling, right? So in stratified sampling, right, we call it as a strata. We divide them into, right, several small groups, right? So anyway, I'm going to come to the example that makes things very easy. So first understand what do you mean by stratified. Divide the whole population into homogeneous groups. Then within that group will be smaller in size, and within that you select the random sample. From each group you do that. Now what is the practical example? So could be, again, I'll go back to the same election example, right? I will not go all around the constituency at random and I'll meet each and every person I'll not do that. Now I'll divide them into the small groups. Maybe this is one option, that's all. You have many options. Maybe the first option, what flashes in my mind first, is that go near a booth. Now you see, people visiting that booth for voting, right, is less. It's a small group of people, correct? So over there you ask the question at random, right? Don't ask everyone, right? So, right, be there for maybe for half an hour. So get randomly 10 samples from there. Okay, so this is because the idea behind the stratified sampling is because whenever you divide the whole large population into a small piece, what happens, maybe it is related to our example as well, maybe that group of people whom you meet are of similar mindset, right? Because that's one area. In that area the problems are common for everyone, So they have a mindset towards a specific, right? Maybe specific person who is there, who's standing for the election, right? Maybe, right? You see that's what we call it as a homogeneous. They have something similar. That's why I went to the booth level, right? Maybe you can do it in any other way also. That's also going to work. But the idea is that divide that into smaller groups, and in the group you do it at random. This is considered to be slightly more effective, right? So I hope the idea is clear, right? So again, the same concept is even being applied in our machine learning algorithms as well. So you see, I just have mentioned here that has nothing to do with the statistics. All right. So we perform a stratified training and testing approach even in the machine learning. So it is related. That's why we are going to study this at a later stage. So I'm just giving a hint that, okay, whatever you are studying now is not going to be wasted. It will be used someday. So, okay. So this is what is called as a stratified sampling. Now, right, the next technique is called as a systematic sampling. In the sense, you have some rule. You will make a rule and you follow that rule when you sample. For example, let's say I have a telephone directory with me, right? The sampling will be done in such a way that, again, so that particular directory will contain...
Excuse me, sir.
Yeah, please.
Sir, in the previous one, can you just tell me the sampling that we are taking from a like a group level or from a booth level? Won't it be a little biased in case of sampling?
No, you will get more accurate data, right? Because that particular group has a particular mindset. You will be able to understand that. If you do it at random throughout the constituency, you may not, because you are not going to get thousands of data for sure. You may get what within that stipulated time, you may be able to get only 100, let's say you, okay, 100 opinions you may get. If you make it completely random, you will never be able to represent the idea behind 1 lakh people by just getting 100 data at random. So the idea is that divide that into 10 pieces. In the 10 pieces, you do it at random. So because that particular location is facing some problem, they have a particular idea. Okay, I should vote only this person. They will discuss and they might vote to the same person. You get actually more detail. That's not biasing. If I do the mistake, that is biasing. I ask only those persons who vote for a particular person. That is bias. Biasing happens from my side. Okay, not from the people's side. I hope that is clear.
Okay, but in that context, that means we will take like we're making 10 groups, so we'll take 100 sample for total each 10 groups.
No. Totally, I still have the time to get only 100, right? Not 100 from each. I'm saying that I may get maximum time to collect 100 views. So what I do, I split that. That's all.
Okay, sir. Thank you.
Okay, so now you see, if you follow that technique, you will get more details. That's all. Your data contains your samples. Whatever samples you collected have more information, right? Maybe more closer information. I don't say it is accurate. Okay, fine. So the next is a systematic sampling, and in case of a systematic sampling, we follow certain rules. So I was trying to give an example of a directory. I still have, let's say the directory contains the details, information of every person, every voting person present in a particular region, let's say. Now, instead of going and talking to people at random, I'll follow a rule. I open a page, every page 10th person I will talk. Maybe, say this is the rule I'm making, right? So every page 10th person, 1, 2, 3, 4, 5, 6, 10, okay. Right? Talk to that person and get his opinion. Next page. See, there is the rule. Systematically, I'm doing. So choosing 8th sample in a sequence. Just an example. Okay, I have a sequence. I select exactly 10th number always, whatever might come. Okay, so this is one technique, right? Again, another version. So I don't go in detail, right? So mostly the stratified one is going to be used widely. So that detail we have. Other options I'm trying to mention here. So the next option is opportunity sampling, right? Opportunity sampling is nothing but you will say that I'll choose first 4 always. Maybe if you go to a booth, you will stick to the same rule. First 4 people voting in that booth, I'll talk. Or first 4 voters which I meet first, maybe, because by the time you go there, it may not be the first 4 voters. Okay, first 4 voters you meet, I will talk. Okay, maybe that's the rule which I follow. That's called as an opportunity sampling. This is also a rule based. You will say that fixed number of persons I'm going to talk. Okay, name given there is opportunity sampling. Then we have another technique called as a reservoir sampling, right? So it's something like how many data points I may get in total, I have no idea. Okay, but I will say that I will select these many number of K samples when n is unknown or n is very large and we have no idea. So this is I can give an example, like how many people will visit your website, I have no idea. Okay, so that's n is unknown, right? But I may say that I will select 10 only. Okay, will it work, will it not work, depends on many other parameters. As of now, that's not our intention. So just think that, okay, I'm going to simply analyze that if, right, I give this advertisement in this particular page, how many will buy my product? Because I have no idea how many will visit that website. I know that, okay, maybe I may have a guess, right? So you see here that falls under the reservoir sample. Okay, systematic one, you read rule based, but you pick a particular one out of the whole thing. Then the opportunity sampling is a different one. You will say that first n numbers I'll choose, last n numbers I'll choose, etc. Right? Reservoir sampling, you have no idea how many total, what is the total population size n, but I'll say that I'll pick k. Right? It can be 10, it can be 100, it can be 1000. Right? K value can be decided according to the requirement, but total how many will come, we have no. So in such case, the sampling technique is called as the reservoir sampling. Okay, I hope the sampling is clear. Is there any doubt with the sampling we discussed so far? Sampling, types of sampling, etc.
Sir, reservoir sampling.
Reservoir sampling. So look at the example, right? Example is like, example will make things more clear, right? So I don't know how many people will visit my website. Okay, so somebody who is going to give an advertisement in my website has to think, okay, so depending on, I'll take a review of many people who are visiting my website, that is K. But totally how many people will visit, no idea, because it's completely random thing, right? Some might search and visit the page, some might know the page and visit that, some might visit it unknowingly, right? Without knowing something, they clicked, they came to this, but they will close it, but count will increase, right? So such kind of sampling, in the sense, what should be the value of K, so that the advertisement, whoever is giving the advertisement will come to know that whether the advertisement giving strategy is going to work or not. They will decide on that. But how many people to choose, that is K. Okay, so that kind of sampling, when n is unknown, how many total data samples they will get is unknown. So such a sampling is called as a reservoir sampling.
Sir, have a network issue.
Yeah.
Hi sir, have
What's
a
the next
network
question?
issue. What is the meaning of K? सर ये है कि हम लोग K क्यों चूज किए K? What is the meaning of K?
K in the sense how many samples you are choosing. Number of samples is K. Total available data is n. Okay, but n is not known. That's all. Yeah. Next question. Any other question? Okay, so we'll go ahead. After the sampling strategies, what are the various properties of the population? So population is the huge collection of the data points, out of which we'll pick some points to get the information, right? The sampling. So where you perform sampling is the, you are going to perform the sampling on the huge data set. We will be referring to that as the population. Right. So the fundamental idea is that I'm going to estimate the complete characteristics of the whole population by just looking at some of the properties of the sampling. That should be clear by now, right? I select few people, I talk to them, and whatever I judge, okay, I'll make a decision. Okay, so most of them have voted this party, so that party will win. You see, you are actually deciding the properties of the whole population who voted, but you are not talking to each one of them to make this decision. So that's what is the idea, right? And that's how we bifurcate population and the sample. First thing. Then what are the various properties of population, right? So there are various properties. The first property is called as a fraction, right? So fraction is something like, out of the population, you guess something like this. Out of the population, how many will vote for a particular candidate? It's a proportion, it's a fraction, right? 10%, 15%, 35%, etc. You see, it's a fraction. How many of the out of the total population will vote for a particular candidate, particular party, maybe, right? So the party vote share at the end, something will come, right? Whenever elections happen. So that's actually a fraction part, right? Now, second one, you see, how many will click the ad if AK is in it? Akshay Kumar is in it, right? If Akshay Kumar is there, people will click on that ad. Maybe somebody will think like that. So you will get a fraction over there. How many will click a given ad if some hero is there, right? So that's a fraction, right? You see here, I'll move to a slightly different case. Now the population is slightly different. I'll come to the differentiation slightly later, but you look at this. So does the aspirin reduces the heart attack risk, right? So looks like yes or no kind of question, but answering is not so easy, right? So you have to consider the population that belongs to two different ways. You need to form the population from where you need to pick this. Okay, so before answering this, let me go back to the previous two examples given for fraction. So how many will vote for candidate X? You have to consider only one population, okay, single one. So how many will click that ad? Again, you see that, yes or no? So one population, few samples from that population will click the ad, you will not click that. Very simple. So that's what is the first two belong to one category. So the next example, if you see, does the aspirin reduces the heart attack risk, right? So just think, what is the population? So the population should be one set, those who have taken the aspirin or not. That is one case. Okay, one set, right, will be, right, have taken the aspirin or not taken the aspirin. So one group will be of that. Second category, you think, right, they may have heart attack or they may not have the, right? So that does not mean they have to take the aspirin only, right? They may be taking other medicines also, right? So aspirin or not is one thing, heart attack is there or not is the other thing. So this is actually a next level. Anyway, we are going to come to solve the problems of many types, right? That will come at a later stage, but this is an introduction. You should be able to understand, right, what exactly is happening, right? So I'm trying to just give an example. So the same scenario with the fourth example, does the covaxin reduces the hospitalization, right? So people who have taken covaxin or who have not taken the covaxin that's one population. Then the other one, those who hospitalized and those who have not hospitalized, right? So two things will come. People who have taken covaxin might get hospitalized, they might not get hospitalized. Whereas other things, right, like those who have taken other vaccines might get hospitalized, so might not get hospitalized. So those are the two aspects in which we need to think, right, before we approach to solve this problem, these kind of problems. Okay, so this is the first this thing. What fraction, right? What fraction is the first property of the population? Okay, moving ahead. The second one is mean. Very straightforward. I'll go quickly over here. So average height of children between 4 to 8. So the word average comes into picture, means it is mean. All right. Average volume of milk packets. All right. So they say it is half liter. Is it really half liter? What is the average? Slight variation will be there, right? Negligible amount, but average can be calculated over there. Next, is the average life expectancy of India is more than that of South Asia, right? So, right, we can think of that. Is the average salary of men and women are different, right? So, looks like yes or no type of answer everywhere, but you see, right, we need to consider, right, a lot of things to what should be my population, where should I, right, how much sampling should be done, still the problem exists over here. All right, so we are trying to define the problems initially before we start solving the problem. Okay, now let's go one step ahead. This topic is considered as a sampling distribution, right? We are bringing the distribution into picture, right? Let us consider a very simple scenario where we have to choose one of the two candidates, right, who are standing in the election. Okay, so let us say one is X, other one is Y. So you have only the whoever is going to vote have only the option to choose X or Y. Okay, so it can be you can think it in this way. X means you are choosing X, Y means you are choosing not X. There is no other option that I don't know. Third option is not. So X you want, you choose X. You don't want X, you have to choose Y. Similarly, it goes with the other way, right? You choose Y means you are voting for Y. You choose X means you want not Y. Okay, so that's the boundary line of this problem. Okay, we are not going beyond that, right? Now, I want to predict who is going to win, right? But the actual probability of choosing a particular person X, right? Let me say that I want to see whether X is going to win or not. Right? So Y means it is not X, that's all, right? So probability of a voter choosing X is unknown, is not known actually, right? So fundamentally that is the problem, right? But if you use a sampling, right, maybe you will be able to make a guess or an estimation. So that's what so the solution starts with the sampling itself. Sampling helps us to make the estimate. Right, so let us say again, this is what I'm doing the sampling like this. I talk to 500 people. Okay, my sample is 500. Okay, N is not the total population, right? N is the total number of people I talk here, right? So sample size is 500, out of which people who voted for X is 320. Right, so now I can make a guess. So you see, it is not P, it is a P cap. Wherever I use a hat, P hat, it is an approximation or it is a guess, it is an estimate. So by default, definitely you will know now how do you do the calculation of this probability. 320 people said yes out of 500. So maybe my estimate is that 0.64 is the probability of X winning. But again, this I cannot say this will happen because I just sampled 5. There are maybe 5 lakh total available, right? So that's the point, right? I'm trying to just make a guess in the initial step, first step, that's all. Right? So if I look at the vote sharing, I can say that X got 64% of the vote, which means Y got the remaining, right? Okay, so now actual question comes into picture. How good is this estimate? You simply said that, okay, 64% is the vote share of X. So is it good? So you see, how good is this estimate? One definite question, right? But in order to answer that, I don't have an actual P, right? If it is, there is an actual P, maybe if it is closer to that or not, depending on that, maybe I should be able to decide something. But since I don't have that P at all, I don't even know that difference, right? What is the difference between P and P? So I told the word good, right? how good is this estimate, right? What is that good stands for? That also I don't know now, as of now. Maybe the word good, actual literal meaning I know, fine. But how good is your result indicates, people say that, okay, if your answer is whatever prediction you have made, right? If it is very close, right? Maybe if you talk about the parliament election, right? Total seats are some 545. If your guess says that 300 to 400, then that's not a good guess. Good guess, according to me, should be very close, like 340 to I say 350, and the actual value come 345. Yes, that's a good guess. See the difference in good. This is my good definition. Somebody else may say that what's wrong in that? 300 to 400 is also a good case. Fantastic. So you see the definition of good changes. So that's what I mentioned here. Need a proper definition of good. How do you decide that it's a good or not good? Also matters. All right. So again, I'm trying to give some inputs to you so that, right, you get adjusted to all these terms which we are going to use at a later stage. Okay, fine. Let's go ahead. Right. Now, this estimate, the P cap or P hat, which I had written earlier, right? That is a estimator, right? That's an estimation of something. Maybe in this particular case, vote share of the X candidate is what I'm trying to look. So that's the estimation, the P cap, small letter P cap. Okay, so just I'll show you the previous slide here. So they see that this is a small letter P cap. Okay, so just note we have a small letter P cap over here. That's the estimate we are talking about. But right, later on we are going to get a capital P cap also. Just bear with me. Right. So now, so we had few questions earlier, right? So in the previous slide, you saw that so many questions are there. Now let me try to slightly modify the question so that it makes more sense. So the question is like this: if we take many random samples with n equal to 500, what would be the distribution of P cap around P? Because P is the actual value, right? I know that once you get the result, you know the P value. Okay, let us say 0.6 is the P value. Actually, the person gets 60% of the votes. That is P somewhere here. Now what I do, I will not stick with only one set of data collection. I sample 500 people, and all the 500 people, I asked a question. They said out of 500, how many? 320, I guess. I forgot. Sorry. Yeah, 320 people said that we voted for X. So because of one set of samples, you decided that X gets 64% of vote. Okay, but I repeat this. Another 500 people I. So this 500 is over. I'm not going to include them again. Okay, so just think that we are not going to ask the same question again with the same people which are already considered. Keep it away, right? Remaining another 500, you take a sample them, ask them a question. You get another value of P cap, small letter P cap I'm talking. Okay, so that P cap might come 0.58. So points, I got an actual value at the center, let's assume that's a 0.6. I got a 0.64, I got 0.58. I can get different such values as you keep repeating this experiment of asking a group of 500 people repeatedly. So that's what is this question. If we take many random samples with n equal to 500, always I ask 500 people, I make that as a group and I do the calculation. Once it is done, go to the next set of 500 people, ask the question, get an answer, make it. So plot it, right? So plot it. Every time you get a P, you plot it. Okay, so that's what we are talking about. So what would be the distribution of the P caps? I get all P caps. Somewhere at the center, I'm expecting a P, right? Like 0.6. I have 0.61, 65, 68, everything you might have received because of the 500 people you ask every time at random. So I might also have received 0.58, 55, 51, 50, 49, 45, etc. So see, a distribution is there, right? That is a question, right? Right? So what is the distribution of that P cap around the P? Hope the point is very clear now. So why the distribution came into picture? It's just because of that. My method of calculating is like that. Okay, let's assume. So because of that, I'm trying to get a distribution. Right, now you see this, the small p cap we have, right? Is it a random variable? Will it vary randomly? Because I'm doing the experiment at random. I'm randomly asking 500 people. So out of the 500 people, right, some will say that, yes, I have voted X. That yes will be very random, right? In first case 320, next case 240, next case, right? Say something closer to 400, next case something closer to 100, etc. You see, it's a random. So because of which I will try to denote the random variable as a p cap. Small p cap is a single value. All values, if you collect, you get a random variable, because that variable gives you all these numbers. I hope that is clear. Now, since the small p cap has an equation, what is the equation? Small letter x divided by n. So small letter x is nothing but that 320 by 500. Next time 400 by 500. Next time 310 by 500. So denominator is still same. It is n. But the numerator is the one which is changing. So that means that is also a random variable. The x value, whatever you get, right? So how many people are saying that I voted for x? That changes. That is a random variable. So you see here that also I changed to capital X. So look at the difference. I'll go back to show you, right? So see here, this is the small letter x by small letter n. That gives you a single value of the estimate, which is p cap. But let us go to the actual equation which we have, which we are using now. So I'll bring the concept of random variable here. That is because the capital P cap is calculated as capital X by n. So this capital X is the random variable, right? Which varies when you change from group of 500 people to another group of 500. They say, a different number of people are going to say that, yes, we voted for candidate X. So the justification is below. Selection of n items from the whole population is also random, correct? So which 500 people you choose, it's a random. So because of that randomness, the result is also going to be random. Are you okay with this? I hope this concept is clear. I am trying to keep it as simple as possible without bringing many equations. Actually, if you refer the textbooks, all the same concepts will be available, but a lot of equations will come into picture where we lose the concentration. Okay, so I'm trying to keep it simple, right? Yeah. So far, what we discussed, do you have any doubt? I would like to clear that first, and then we'll proceed further. Okay, any doubt with whatever we discussed in this particular session? All right, so let's proceed further. Right, so the next point says that hence the estimate p cap, right, equal to p cap, in the sense that random variable p cap, capital P cap, taking a specific value 0.64, where 0.64 is my small, right? So the random variable capital P cap taking a value of specific value 0.64, 0.65, 0.13, 0.38, etc. right, is a random variable sample. It's a sample, correct? Are you okay with the sampling? Because I have so many values present, possible values for the capital P cap, like 0.65, 0.58, 0.69, out of which one of them I'm picking, right? So that's why it is said to be the sample. That's the sample. One sample I picked out of all the possible 500 people, right, who can give you a prediction, right? I picked only one of them and I got 0.64. Is that right? So that's why I said it's a sample. Right. Now you see which kind of variable it is, right? It's a binomial case because yes or no type, X or not X, right? So just recall what we discussed earlier, right? So binomial is a case where you have yes or no type, 0 or 1, increase or decrease, right? Like that. If you have your data set of that type, this is going to be the binomial case. Right? Anyway, we don't have to go in depth about that, but little bit of mathematics is necessary over here. I cannot avoid. All right. So because of that reason, I'm bringing right this concept. Few of the equations I'm directly borrowing from the properties of binomial random variable. It's a distribution itself. Just think in that way. Now, I have a random variable, right? which means you can calculate the mean of that, the variance, and the standard deviation. So three things we can calculate straightforward whenever you have some equation, right? For example, in the previous half of today's session, we discussed that, okay, this is the f of x for a given distribution. For that distribution, you can do the mathematics and you can find what is the mean, what is the variance, what is the standard deviation for each and every one, each and every equation we choose. Okay, I showed few equations only, but there are many other equations as well. For each and every such equation, you can calculate. You can calculate what's the mean, you can calculate what is the variance, you can calculate what is the standard deviation. But out of this, all these, I'm sticking to only one now because we understood that, okay, this particular case belongs to the binomial. So mean, let us calculate, right? It's a very simple calculation. So I have pasted here because if I simply write E of P cap equal to P, I think people find it difficult to understand how. So, right? So that's why I'm writing. So this is the E stands for the expectation. The expectation is the mean. What's the chance of getting something, right? Is called as a mean. Yes.
सर थोड़ा बैक साइड करिए क्योंकि थोड़ा नेटवर्क इशू के अंदर okay.
All right.
Okay. Okay.
So we are calculating the mean. Okay, the expectation. Mean is, in other words, it's an expectation. So the standard notation is E of P. All right. So more details about how this calculation happens, etc. in full detail we are going to study when we discuss the probability, but as of now just bear with me. Okay, so P cap is capital X by N, so I replace that. Now for a constant value there is no expectation, so constant is 500. This 500 is there for every number, right? So that can be taken off. Okay, so you see E is expectable, E is given only to X. Okay, divide that by N. Now you see, again, this derivation we will be using it at a later stage. So just remember, E of X for a binomial is NP. N is the number of samples into P is the probability. So we have NP, E of X equal to NP is the only thing which you may not know. Okay, so just for the time being, just remember this. For a binomial case, E of X is equal to NP. Mean is equal to NP. So N cancels, I am left with P. Okay, so that's how we calculate the mean of this particular case. Yes, somebody asked a question.
Sir, what is E of P? What do you mean by E of P?
Expectation. Mean has other name, expectation.
So many P. What is P and normal? So there are many things in E of P. Many very values in E of P.
P cap, whatever we given as a capital P cap, right? So they have many values, correct? 0.64, 0.65, 0.85, 0.15, 0.3, many values you have, right? I'm taking the mean of that. That's all. Okay. It is a mean, simply mean. So equation, if you feel it very difficult right now, don't worry. Simply think that it is a mean of sum. Okay. Fine. Yeah. Any other question?
And E of X is well, we are selecting a particular value and that value of E of X. What is E of X? How can we calculate? I do not recognize.
No problem. I'll tell you. See, what is the value of capital X? It is a number of people who say, yes, I voted for capital X. That's the person. So that will vary, right? Out of 500, once I read first 500 people, 320 people said, yes, I voted. See the capital X equal to 320. Next time when I go for a new batch and I ask 500 people saying that, how many of you voted? Only 100 people say, you see capital X equal to 100. Are you getting? So that's the small, that's the capital X. Okay, it's the same. So expectation of your capital P is same as expectation of X divided by N. But for a this particular case where you have binomial, E of X equal to NP, right? This is directly taken from mathematics, where where we are going to study the probability part, there we have this equation. Okay, as of now, we are not discussing that part, so I have directly taken from there and I have substituted. That is equal to NP. So N cancels, you are left with P. So mean of this is P itself. First thing. Similarly, we can calculate the variance. Variance is denoted by sigma square of P. Okay, so P cap is denoted by once again X by N. Now we have to follow the rules of mathematics. Whenever you are calculating the sigma square, if you have a constant, that constant comes out with the square term. You see, it is X by N, it was there, it came out as N square. Since it is in the denominator, it is 1 by X square into sigma square of X. Now, again, I will use the properties from mathematics and I'll substitute. Sigma square of X can be simply written as N into P into 1 minus P. So what you see here, N into P into 1 minus P, right? So this part itself is the sigma square X for the binomial variable. If it is binomial variable, this is straightforward. I have to use this, which is already proved. Okay, so now you see N and one of the N cancels. I'm left with P into 1 minus P divided by N. So that is the variance. So variance you understood already. We have discussed the variance, right, from the mean, right? How much is the spread? Similarly, we have a standard deviation, which is the square root of this. So you take a square root of this and you get that. Okay. All right. So again, we have one theorem that is coming up from where we can come to this. As of now, don't worry. As the N increases, any distribution tends to be normal. Somebody has proved that. That's called as a central value theorem. Right? Anyway, we are not going to touch that as of now. Don't worry about this particular point. Right? So what we observed is that the P cap is centered around P. Right? P is the actual value. Whatever P cap you obtained from your experiments, right? I repeated the experiments many times by asking different 500 group of people, and each time I calculate a P cap, I'll try to make a distribution over there. What I can understand now is that, right, this observed P cap is centered around P. Why do you say that? Because my mean is P. Mean means the center, right? Actual value is P. Actually, how many people voted out of all the voters is P. I don't know. So what I did, I took groups of 500, and I kept asking people, how many of you, right? Now what I came to know is that my P cap values, whatever I got, it is actually distributed around the actual P. Actual P is here, P caps are around them, correct? So it will follow a distribution, right? What is a spread? Spread in the sense you can see that this term I'm talking about, again, P into 1 minus P, I'm not considering. I'm taking that because there is a constant root of 1 divided by N I can see in the denominator, right? So that I am using as a proportionality control, right? It is dependent on root of 1 by N. Okay, so it's proportional. If you are saying that why did you left P minus 1 by P, no problem, you can consider, no issues. All right, so P into 1 minus P divided by N. So since P and 1 minus P, right, the probabilities you can neglect, doesn't matter, still you have left with 1 by N, which is a constant. So 1 by root N is the controller. So that is still valid. But those who say that, okay, no, I don't understand, why did you left P and 1 minus P? It's absolutely fine, you can take it. Okay, so now we are able to come a little bit closer to the answer, saying that, okay, if I'm able to, from the P cap, somehow if I'm able to calculate the P, then that's the answer, right? That's the actual answer, saying that, okay, P is the probability, right, of people selecting X, right? But I don't have a P. I have P caps available with me. Many times I repeated the trials by asking, say, 500 group of people to get the various P caps. From the P caps, I get a bigger P cap, right? That is a random variable, which all the possible values your small P cap can take. Okay, so yes, please go ahead, ask any question if you have, right? Because maybe this is a little bit of mathematics included over here. So don't worry about the equations, right? How did that equation come? No issues. As of now, nothing to it. So concept you need to understand here is that how I'm creating a distribution, relate the distribution to one of the graphs we studied earlier, right? Looks like a graph for me. I can able to get the central value. That is the actual answer. That's what I'm saying. Okay, just try to come to that level is sufficient. No need to worry about what is P cap, what is X cap. No problem. Okay. Yeah. Any doubt?
So just to summarize that, so when we say that capital P CRO is, I think so, lot of different, you can say, mean that we have carried out for the sample.
Okay.
So we want to say is that whenever mean is there for the mean for all that would be equal to our actual value.
Yeah. So if you are able to create a distribution, right, then the actual value of P will be the mean of all the P caps you have got. Okay.
Right.
Right. That's the point. Again, it may depend upon the accuracy may depend upon how many times you repeated the experiment. Okay. I cannot say that, oh, I did the experiment 3 times, but still the mean is varying. It's not sufficient. Sampling is not sufficient. You have to go for higher values. Okay, so that's the point. Ultimately, right? That should
Right.
be that is what we should understand from this. Okay, I hope that is clear. Any other doubt?
Right. So in case if the population is 50,000 and we need to do a sampling on the data and I take 5,000, so do I need to cover entire population for sampling, or I can consider 80% of the population and for sampling
No.
and get?
Normally, we don't even touch the 50% level. No, we don't.
Okay.
So go for a smaller size like 50, 500, maybe repeat it 10 times. Maybe that is sufficient. Okay, don't go. Nobody has a time to do all those things like up to reaching up to 60%, 50%. No, consider the whole Indian population, for example. Okay.
Right.
So you want to do a analysis of the poll means no, people won't even touch the 20%, I guess. Okay, because 20% of 1.2 billion is too much, right? Nobody has that much time or resources to do that. Okay, so smaller numbers should go. Okay, but we have to do it efficiently. That's what is the meaning. Okay. I hope that is clear.
Yes.
All right, so let's quickly go ahead and let's try to do a calculation. Again, this is not a perfect answer. We don't get a perfect answer. Don't expect as of now. I just wanted to bring some little bit of mathematics so that we get adjusted to it. So let us say there is a p value which is equal to 0.66, which is the actual answer. Let us assume. Okay, right. Now I can calculate a sigma of p cap, right? So how do you do that? You apply the formula. Just now we have seen that, right? So sigma p cap, the standard deviation equation which you see here, right? Sigma p cap equal to p into 1 minus p divided by n. So taking the same values, p is 0.66, 1 minus p will be 0.34, and n is considered as 500. So you see that this is the answer, standard deviation, right? Now this was the mean, and now you see this is the standard deviation. So it means if you, as you are going to increase the number of samples, okay, so sample, repeat that more number of times, and whatever values you get, you connect them. You don't make it just discrete points, try to connect them. Right? When that happens, you may get a graph like this. That's what you see. The central is 0, right? You will get something like, right? There is another procedure. You need to do a normalization, etc. But anyway, let's not go to that as of now. So we can anticipate the p cap to follow the normal distribution with a mean of 0.66 and a standard deviation of this. Right? So this is the mathematics behind that. But still, now you see, as of now, I still have a p cap values only. I don't have a p. I don't have a p. I said that, okay, using this, you calculate, you go to the mean, and it is expected that mean becomes your actual value. There are some conditions. The conditions already we mentioned include, you should have sufficiently large number of samples, right? Whether you have done that or not, that does, as of now, we have no idea. Fine. But still, right, if at all the actual p was 0.66, let's assume, right? If at all it is that, then this is what is the conclusion. Because I know the p, I will be able to calculate the standard deviation and I will be able to get a graph. That is possible, right? If at all you know this, but still the question remains, how do you get to this? I have no idea as of now. So we have to discuss few more concepts over there. Okay, few more concepts will take us till there, right? So we have an answer, but as of now, no. So in this case, no, I don't have an answer to P. Okay, so whatever estimates I have, yes, I am fine. I know the equation. I know which particular graph it is going to follow. What is the distribution, etc. Fine, right? But P value we don't have. Just remember. Okay, let's proceed.
Hello, sir.
Yes.
Can you go back, sir? The
Yeah.
slides.
This one or the
Sir?
previous?
Yeah, this one, sir.
Yes, yes.
This
please go ahead.
is this sigma capital P cap. Then 0.66x 0.34. Where we have got this value, sir?
Yeah, I'll go to the previous slide. You see, there is a equation. Equation says that this is the equation. You are finding the equation?
Yeah.
P into 1 minus P divided by N. Okay. So you see the equation. It says that let the P is equal to 0.66. Okay. So that 0.66 we have substituted here. Multiply that with 1 minus P. 1 minus 0.66 is 0.34. Okay. Fine with the 0.34, and 500 is the number of samples we have. We are still solving the same problem. Okay, so what was the problem? The problem is this one. Okay, so you see the N value is already given as 5. This is the still same problem. We have not diverted from that. We didn't get an answer to that. So we are still solving the same thing with the concept. So I'm bringing a concept, we are solving the problem. Next, another concept comes, we learn something, we apply that. Okay, like that it is doing. Okay, I hope that is clear. So
right, sir.
That's how we substituted the values. So equations are already known to us. It is assumed that we know all these equations, but still I try to write the equation in a short fashion. All right. Okay, so whatever we
सर
have.
एक क्वेश्चन मेरा है सर एक क्वेश्चन 0.34 कहाँ से आया
1 minus P. 1 minus 0.66. Equation says P into 1 minus P, right? Okay.
Okay.
Right. So,
sir, we have assumed the value of P is equal to 0.66.
Yes.
Because still we need to find it.
It is assumed. We have not. I just shown that, okay, if at all the actual P is 0.66, then this is what is happening, right? But at the end, you see, I clearly mentioned, we don't have the value. I don't have.
So this is our assumption.
This is something like, see, the previous case, when we solved the problem, right, we said that the P value came to be how much? Sorry. See, 0.64, P cap. P cap is an estimate. Estimate came to be 0.64, right? And also we understood that this P cap is always around your actual P. So I took a closer value to this. 0.64 is the estimate. Let us think that, okay, actual value may be 0.66. So I simply said that, okay, let P is equal to this. If at all you know the value of P, yes, this is what you can do. You can write a PDF format. Distribution can be drawn like that. That's what is the calculation says. But at the end, you see, I have clearly mentioned, I don't have the value of P. So finding that is a big job for us.
Right.
All right. Okay, fine. So let's see. So whatever we have done so far is actually falling under a case that is called as a deductive reasoning. In the sense, I'm sampling, right? I'm trying to create the distribution over here. How do you do that? You start with a large population, like 50 lakh people, 5 lakh people, right? Then take a smaller number, say 500, 100, 50, whatever. Take a sample, ask the question, right? Understand what they have done, what is their vote share, etc. Leave it. Go to the next one. So you see, it is a repeated sampling. This is what we have done. We had a large sample initially, large population. We repeated the sampling, estimated the properties of each case. Like again, we may have obtained a fraction like 64%, 68%, 32%, 20%. So you see, from that small group, you estimated the properties. You may go with the fraction, mean, etc. Right? In this case, in the example, I was using the fraction part, like 0.64%, 0.64, 64%, and so on. from those values, we will try to get a distribution, right? This is what we have done so far. So this particular whole procedure, what we followed, is going to be called as a deductive reasoning. You had a bigger population, divide them into smaller pieces, and you process. So deductive. There is another approach that is called as a inductive, right? Inductive. I'll tell you. This is important, and this is actually this is also going to be used. Both will be used. I don't say that you have to follow this only. You leave the other one. No, it's not like that. So think a scenario wherein let's try to keep it. Okay, let me give an example for the same thing. The election process. You want to make the guess who is going to win. Still the same problem. But let us say that I don't have enough resource or enough money to collect the data. Let's say all I can afford is only one sample. In the sense, I can go for a 500 people and I can ask. That's what I can afford. Let's see, because it takes money, time, many things. I have to, if I want to do that for say 50 such different groups, 500 samples, ask the question, leave it, go to the next one. Like that, if I want to do that 50 times, I need money, I need time, etc. Let me say that I don't have. So I have time or money for only one. So that's what is the first point. Start from one set of observation. You start from the lowest point, right? Previously I had big, I actually came down. Now I start from a point where I have very less, like only one, right? You are supposed to investigate what we can conclude about the system which generated this data. In the sense, out of those 500, say 300 people said that, okay, right? So we voted for X, right? So that's what is the information you get. From that, what you can judge about the whole population is the question. So that's the second point. Investigate, and you need to do an investigation, right? What you can conclude about the system that generates. System means what? It is the whole population which generated that, right? So from that whole population, this is the one part of it, and I actually asked the question and I got that answer, right? So I'm doing the reverse now. So from one, I'm trying to go back. So looks like a detective work. That's why I mentioned, right? It's a detective work. I start with only one piece of clue I have, right? I have to, right, get to the top of that, right? By doing what is called as a detective work. What does the data tell us? It's not only the problem here, it's the same. Remember this question. We are going to solve the same question irrespective of what problem you have in the data science. Ultimately, I have some data. You do a EDA, you do something, some pre-processing. After that, the question is, what is this going to tell you, right? What is this data? Ultimately, what is it going to tell us? So you see that's why the statistics is the first part of our whole data science course in mathematical view. Okay, programming anyway, we know that we can do programming even in other methods, but mathematics begins here. So that's why we are studying as a first step in this, the statistics. Okay, so we are going to do this in the upcoming sessions, right? So this inductive reasoning is what will be starting, right? So maybe in the next class. All right. So do you have any doubt?
Sir, what is the basic difference between inductive reasoning and deductive reasoning?
Yeah, in case of a deductive, you take many number of samples. 500 samples are repeated many times. Here, that's not a case. Only one time I can read the 500 data. Okay, so
which is better, sir? Which
no,
is better for a conclusion?
I already answered that question. There is no better. Both are useful in their own way.
Okay.
Okay. It's not like you are comparing and telling something good. That's not the case here. There are two approaches. That's okay. Yes. Any other question? Okay. So I hope this session is useful to you, and thank you for your patience. We'll meet tomorrow, same time, and continue from here.